In previous JavaScript beginners tutorial, we have discussed all the fundamentals and the basics of the language. Here in this video, we discuss important JavaScript concepts like closure, execution context, how JavaScript engine works, lexical environment, scope, recursive functions, etc. Unlike the fundamentals, these topics are a little hard to understand for beginners as well as experienced developers. So in this video, I have explained everything in depth with proper diagrams and sample code snippet. I'm sure you will find this tutorial helpful, so please watch till the end of the video. In this session, we discuss JavaScript closure. Most of us finds this topic confusing. Everyone wish if it were more easy to understand because it is one of the fundamental concepts regarding JavaScript functions. I have spent a lot of time making this video, so if you find this video helpful, which I'm sure of, please consider subscribing to this channel Code Affection. Please like and share this video with your friends and colleagues. First of all, as a prerequisite to JavaScript closure, we have to thoroughly understand what is scope chain and lexical scoping. As you know, scope means availability of a variable or a function. We have already discussed the scope of variables declared with various keywords like let, const, and var. Now, let's discuss availability of a defined function. Consider this function A. It is defined in global scope, so it will be available throughout the global scope. Now, let's enclose this function within a block statement like this. As you can see, still this function is available outside this block statement. So a block statement does not limit the availability of a function to the outside. Now let's enclose this function within another function. Let's call it as function parent. So here we have nested this function A within this parent function here. So such types of functions are called as nested function, and this outer function is called as parent function, and the functions within it is called as child functions. As you can see, this child function A is not accessible to outside this parent function here. Now let's move this function call to this parent function. Now we have to call the parent function after all. Now this child function is getting executed with this function call here. So a child function is only accessible within its parent unless if you return the function. If you return the function can be assigned to an outside variable and can be invoked anywhere as long as the assigned variable is available. So that's a different case. We'll be discussing such functions along with JavaScript closure. So far, based on where the function is defined, we have discussed the availability of the function. From now onwards, we're gonna discuss scope of variables defined within the function using the terminologies scope chain, lexical scoping, and closure. Now let me remove this parent function here. Now inside the function, let's declare a variable y and let's initialize that with 2. Now let's print the same here. This local variable y is only accessible within this function here. But there is also an exception. If you return this variable y, its value can be accessed outside the function. There is no complication regarding returning a variable from a function, but if you return a function within from another function, then there are some complications. We're gonna discuss that along with closure. For now, we have a normal function. Now if you try to access this variable outside this function like this, as you can see, it's not possible to access local variables of this function outside the function. So let's move this statement back to the function here. Now let's talk about scope of this function here, meaning what are the variables that can be used within this function here. Of course, local variables or parameters for the function are always accessible within the function. Now suppose we have another variable x outside the function. So outside this function here, we have global scope. So this x variable is within the global scope. Now if you try to access the same within this function here, it's possible to access global variables within a function. To put this into a statement, we could say scope of a function is the sum of its local scope and scope of outer function or global scope. For this function, the outer scope is global scope. As mentioned, when a function is nested within another function, the outer scope will be the parent function scope. We're gonna see that in a bit. So this is how internally JavaScript manages those function scopes. So here we have the function A and the corresponding local scope is represented within this block here. Inside the scope, we have a single variable y. The outer scope of this function is global scope, which is represented with this block here with within it we have a single variable x. Now inside these scopes there will be a reference to its immediate scopes. So for this local scope, the immediate outer scope is global scope. So here we have the reference to it. In any case, there won't be another scope outside global scope, so that's why we are not seeing a reference like this here. So this is how a function manages its scope. All of its outer scope and local scope are interlinked with a reference like this. Now inside this function, let me declare a child function, inner function. Inside that we have a single variable z initialized with 3. And let me rename this parent function as outer function. So here we have called the parent function here. Now inside the parent function, let's call this inner function or child function. Now let's discuss scope of this child function here. As we already stated, scope of a function is the sum of its local scope and the scope of outer function or global scope. So inside this function we can access its local variable without a doubt, so which is z. As per this statement, scope of the nested function can be represented like this. Here we have the inner function or nested function, and this block here represents its local scope. Inside that we only have a single variable z. Now the scope of this function is the sum of its local scope and the scope of outer function. Now this block here represents the scope of the outer function. Inside that we only have this single variable y. Now the same statement is also applicable for the scope of this outer function also. Here we are considering the scope of the outer function, which is then added to this local scope of this inner function. So scope of this outer function is its local scope plus its outer scope. So for this outer function, its outer environment is global scope. So here we have the global scope also. Inside that we have the single variable x. So scope of this inner function is sum of these scopes here. All of them are interlinked with a reference like this. Now this chain of scopes, or you could say sum of these scopes in this hierarchy, is called as scope chain. All of them are interlinked with a reference like this. So this is what we call as scope chain. In previous example also we have a scope chain including local scope and global scope, which is interlinked with this reference here. Now back to the program. When we say scope of this function is sum of this local scope and outer scope, means we can access all of the variables in those scopes here. So we can access y here. You could see its value printed. You could access the global scope also. So that's what we meant by the scope of a function. So in this way, this function can make use of its local scope or its outer scope in the scope chain. Now before discussing JavaScript closure, there is one more important topic to be discussed, which is lexical scope or lexical scoping. Now let me comment this function here. We will get back to this later. Now consider this program. We have a variable a. Now let's define a function to print the value of this variable a. So here is the function print a. So here we have the log statement. Within it we just need to print the value of a. Now suppose by mistake we are defining the same variable a inside this function itself. Now if I call the function here, what will be the output? Will it print 0 from this outer variable a or the inner variable a with 1? Now let's uncomment this. You see it is printing the inner variable a 1. It's because of lexical scope in JavaScript. That means scope of a variable is determined at compile time based on the location where it is defined. Whatever the value of this variable a, this function print a will always print the value of this inner variable a here. Here we have two variables with the same name a. One is declared in global scope, one is locally declared to this function print a. Now when we access the same variable a within the function, it will be always referring to the local variable a here. That's what lexical scope. Variables are mapped to the declarations based on the location where it is defined in the source code. The process of mapping a variable name or identifier name to the declaration is called as lexical scoping. And this process is done at compile time because JavaScript can easily determine which variable is referring to based on the location where it is defined in the source code. So that's what we have here, the process of defining how variable names are resolved or map to their definitions. So that's what we have meant by lexical scoping. The exact opposite of lexical scope is dynamic scope. JavaScript is a lexical scoping language. There are some languages where variables are mapped to their declarations based on where they are invoked rather than their declaration location. So it can only be done at runtime. So that's what dynamic scope means. Now if I remove this local variable a here, then it will print the outer variable a because there is no other variable a to map to. Now let's explain lexical scoping with our previous example. So let me get rid of this and let's uncomment this program here. Currently inside this inner function we are accessing the variable x, but it is defined in global scope here. It's nowhere defined inside these outer function or inner function. So during lexical scoping, the JavaScript engine checks whether this variable x is defined locally to this inner function here. No, it's not defined. Then it will go to the immediate outer scope of the function as mentioned in this scope chain here. If the variable is not here, then it will go to the outer scope. The variable x is not present here, then it will go to the outer scope here. So that's how scope chain works, and this process of mapping this x variable here to this declaration defined in global scope is done at compile time. So the process of lookup will be like this. Here we have the inner function and we are calling the variable x here. There is no local variable with the name x. Then it will go to the outer scope. There is no variable x and it finds the variable x in global scope. Now consider this as case 1. Now here we have the case 2. We are declaring the variable x within this outer function along with the variable y. So here we are defining the variable x and let's initialize that with 11. Now this time this x is mapped to this parent variable x here because in this scope chain the parent variable x comes before the global variable x here. So based on the location where these variables are defined, JavaScript determines which x is referring here, this one or this one. Now here we have the final case. We are swapping these two functions, inner function and outer function. See, here we have the inner function in between global scope and outer function here. Now let's modify this program accordingly. Let's move this outer function as a child function to this inner function here. Now let's change this function invocation order. So this time order is different. See, this time it prints the outer variable x value 1. Since the order of the function is changed, the variable is getting accessed even before this function outer function, which is the child function in this case for this function inner function. So this x map to this outer scope x here. So this is how lexical scoping of variables works based on the location where they are defined. These are the prerequisite topics for learning JavaScript closure. Now with what we have learned, explaining JavaScript closure becomes more easier. Let me get rid of this existing code here. Here we have this function fun. Inside that we have a variable a initialized with 1. Now we have the child function print a. Here we have the log statement. Now let's call the parent function here. Now inside the parent we have to call the child function print a. As a result of that, this parent variable a is getting printed here. Now instead of defining and invoking this function here, I'm gonna return this function from this parent function here. When returning a function like this, I prefer returning anonymous functions like this. The same function will be returned while invoking this function here, so we can access the return function with a variable like this, print a. Now you see, we can call this print a function, which is actually this return function from here. It can be called anywhere inside this program, even after 1000 lines of code. As long as the variable print a is available, this function can be invoked without a problem. See, in this return function here, we are accessing the parent variable a. In previous case, we have defined the function here and we call the function inside this parent function itself. But now instead of defining and invoking the function inside the parent, we are returning the function. So with this statement, the parent function is getting executed and this function is returned and it is assigned to this variable. Now when we invoke the function, say after 10,000 lines of code, print a is invoked here, the value of a is getting printed here. How is it possible to access the value of this a when it is defined in the parent and the execution of this parent is done with this statement here? How is it possible for this function to access this variable a defined in the outer function here? Is it a ghost? So that's what I'm being doubtful. Don't you feel the same? So that's where JavaScript closure comes into the picture. Since we have learned lexical scoping, you might be thinking this variable A is referring to the outer scope variable or parent function variable A. If you think so, you are 100% correct, but it is made possible physically through JavaScript closure. The concept of lexical scoping is a rule which explaining how things should be working, but through JavaScript closure it is made possible physically. JavaScript closure gives the access to this variable, outer variable A, even after the outer function execution is over. So here we have the official definition from MDN. A closure is the combination of a function bundled together or enclosed with reference to its surrounding state or lexical environment. Pictorially, you could represent a closure like this. It is a bundle consisting of function body or function definition along with the variables that this function is depending upon. The data structure that hold the depending variables are called as lexical environment. Now back to our program here. In JavaScript, every function has a closure. For this return function, there will be a closure. Inside that closure, this function definition will be there along with the variables it is referring to. So in that closure, a reference to this variable A will be there. So that's how this function is able to access the value of A even after thousands of lines of code here. So that's how a function closure remembers external things that is used in the function. The required variables will be preserved in the corresponding function closure. It's like a backpack. Wherever you go, it will be there. So no worry, function carries everything it needs for its further execution. Now talking about this lexical environment, it's actually a data structure holding these variables required for this function. Don't think that both lexical scoping and lexical environment are same. Lexical environment is a data structure that holds identifier mapping information, and this mapping is defined through lexical scoping based on the location. That mapping is physically stored in lexical environment. So basically, which is storing the dependent variables for this function here. Now actually I can show you this closure in developer console of the browser. For that, first of all, we have to put a breakpoint inside this return function here. So inside this developer console, go to the tab sources, then put a breakpoint here. Now let's reload the application. So currently we are at the breakpoint. Now under this scope here, you could see this closure containing the variable A. With this statement, the parent function gets executed and this anonymous function is returned to this variable. And now JavaScript is in the process of executing this function. Unfortunately, we put a breakpoint inside it, and now here we are. Even though the parent function execution is over with this statement, since the return function is depending upon the parent function variable A, the closure contains a reference to the variable A here. So that's how this closure works. Now hope you are convinced with my explanation. Now do you have this doubt? Does JavaScript closure is only available to nested functions like this? No. Every function in JavaScript has a closure, whether it is nested or not. Everyone explains closure with nested functions because it is easy to explain the concepts. Now to prove my statement, let's remove this debugger and back to the program here. Let me replace this function with this increment function here. First of all, we have this counter variable. Here we have a simple function increment. Within it, we will increment the global variable counter and it is getting printed to the developer console here. So that's the simple program here. Now let's prove my statement that every function has a closure. To prove that, there is a straightforward method by just calling this console.dir function. Inside that, just pass the function name, which is increment. Now this function can display interactive list of properties specified for the JavaScript object. As you know, JavaScript functions also comes under the data type object. So we can call this function to see what is really happening inside the function. Now here we have the interactive list of properties of the function. Now this is what we are talking about. Under this scopes, you could see various variables that is depending upon. Here we have two scopes that this function increment is depending upon. Now if you expand script, you could see the dependent variable counter here. Now I'm running this JavaScript file commonpractice.js within index.html. Since I'm using a script file to run this JavaScript code here, whatever variables from this file will be listed under the scope with the name script. If you are running this JavaScript code within an HTML directly, then the variable counter will be there under this global scope here. So this variable counter is shown as part of the function closure. So that's kind of prove my point. I know you are not fully convinced with my explanation. For that, I'm modifying this program to modular design pattern. Don't worry, it's not that complicated. I will give you the necessary brief introduction and we'll be discussing the modular design pattern in a separate session in future. So within this HTML, we have referenced this script file script.js. In my case, I'm using a different name for this file. Most of you might be using this name script.js, and here we have another file counter.js. Within it we will paste the function that we have just created, which is increment function. Now if you look at this definition of the function, along with the function here we have these keywords export default, so that this function increment can be exported from this file counter.js and it can be imported in another file for further use. So that's what we have done within this script.js file. Import increment function from this given path file. You see, just beneath that we can call the function like this. So that's what modular design pattern works. We can import functions or objects that is exported from another file. So let's do that here so that you can clearly understand my point. Now let me cut this function from here and let's paste that inside our file counter.js, which I have already created, and let's paste the function here. Now first of all, we have to export this function from here. So we just need to do this export default. So here we have exported the function increment. Now let's import the same inside this import increment from counter.js. Now let's call the function here increment. And also I forgot to mention something. Inside the index.html, while referring the script.js file path, inside the script tab we have to add this attribute type is equal to module. It's part of modular design pattern. I just want to know you this, whatever we have done here is completely legit. I'm not using any external package. It's completely possible with plain JavaScript. We'll be discussing more about modular design pattern in upcoming sessions. As you can see, the function is working and this function is getting executed twice. It's because we are calling the same function here also. So let's remove that here. So we have defined the function increment and it is exported from this function counter.js, and the same function increment is imported inside the script file and we can call the function whenever needed. So that's how modular design pattern works. Now to prove my point, I have to place a debugger inside this function here. So go to source tab. Let's expand this developer console. Here we have the files, and inside this counter.js file we have the function. Let's put a breakpoint here and let's reload the application. Now under this scope we have local, which is local scope. Since we are using modular design pattern, we have a scope called module. Inside that we have the function increment along with the dependent variable counter. As we can see, the variable is declared within this counter.js file and which is made available for this exported function increment when it is invoked here. And also inside this scope, it's not always necessary to list closure variables under the name closure. It only happens for nested functions. Otherwise, like we have seen before, and this time it will be listed under different scope names like module or script. So wherever this function is made available, whether it is returning from a parent function or whether it is exported from a file to a different file, the dependent variables are remembered through the function closure like this. So hope you are convinced that all functions has closure to remember dependent variables. Now let's get rid of export and import. Let me cut this and pasting here, and let's remove this export keyword. Now here we are back to our previous program. Now do you know why JavaScript closure use the word reference to surrounding state rather than value of surrounding state? Now that's also an important topic to be discussed. So back to our program here, and let's create a function to generate counters. So we will define this function generate counter. Inside the function we have this variable counter and which is initialized with 0. Now we have few functions for incrementing or decrementing or displaying the counter value. So these are those functions. All of them are defined with arrow syntax. So first of all we have increment, which is just to increment the counter variable here, and then we have decrement for decrement the counter. Set function is used to update the value of the counter, and finally with this display function it will just display the value of the counter. Now we have to return all of these functions here. So all of them can be returned together with an object like this. So increment is equal to increment function. When the assigned component has the same name as that of the property here, then we just need to do this: increment, then decrement, set, and display. Now we can create counters with this function generate counter. So here we have the first counter, counter 1. We just need to call the function here, and all of these functions along with this variable will be returned. Because all of these functions are using the variable counter, so the closure of these functions will include the variable counter. So that's what we have learned so far. Now to see the value inside the counter variable, let's call the function display. So counter1 dot display can be called. Sorry, I forgot to mention the keyword const here. So to do that in a one step, you just need to place the cursor at the first line and just use the shortcut hold Control then Alt, then use the downward arrows like this. So then all of the lines in the same cursor place will be selected. Now we just need to type const. Okay, we have called the function display. As a result of that, the value of the counter variable is printed. Now let's increment the variable. For that we can call this function increment. After the increment, the value should be updated to 1. To see that, let's move this display statement after increment. Now you could see the value as 1. Now let's decrement the incremented value. It is again back to 0. Now let's set that with a given value. Call the function set and pass the value here, something like 10. Now from these function invocations, it is clear that all of these function closures has a reference to this variable, not the value of the variable here. That's what we have seen here. After calling the increment function, the value of 0 is get incremented to 1. Then the same variable is getting decremented after calling the decrement function. Suppose if the function closure has value of the counter instead of the reference, initially all of these function closures will be having the value 0 like this rather than the reference. So when this function increment the variable 1, it will only happen at this function increment here because it is having the value rather than the reference. So that's proved the point. Closures remember the variable through reference rather than the value. Now let's remove some of these functions here. Now let's create one more counter, and this time we will call it as counter2. Now let me copy this and pasting here. Instead of increment, we will call decrement. Now let's change counter1 to counter2. See, here we have created two counters, counter1 and counter2. With counter1 we have called the function increment, so the value is get incremented to 1. Now with counter2 we have called the function decrement. You see the value is getting -1 because 0 is getting decremented to -1. Now my point is that these two counters has created different closures for these functions here, because we have called this function generate counter separately for creating these two counters here. So this function invocation here will create a separate closure for these functions here, and here we call the function again, so these return functions here will have a different closure. So that's what we have seen here. Let me remove this decrement statement. We have incremented the counter. The value of counter1 is displayed as 1. At the same time counter2 is 0, so which is not incremented with this counter1 increment function here, which is clearly mentioned after the definition. Closures are created every time a function is created at function creation time. So each time we call this function parent function, these functions are created with this return statement here. When we call this generate counter each time, it creates separate set of functions with this return statement. So that's what happens here. Both these functions create separate closures. Now to prove the same, I can show you another example from MDN. For that, first of all, let me comment this one here. We will get back to this example later. Now let's copy this example from MDN. So here's the function makeAdder, which is a parent function. It has a single parameter x. Inside that, an anonymous function is getting returned. The return function also has a parameter y. Inside the function, both x and y is getting added and the result is returned. So the function is invoked twice here. makeAdder with 5, makeAdder with 10 is invoked here. So currently inside this variable, there will be a function like this. So currently the closure x is having the value 5. Now when we call this add 5 here with this parameter 2, then 2 plus 5 returns 7. Here the same function makeAdder is again called with another value 10. As I mentioned before, each time the function is created with this return statement, a new closure is created. So this time inside add 10, the created function will be having a different closure with the value 10. Here we have called the function add 10 with the same value 2. So 2 plus 10 returns 12. So each time we call a function, it creates a closure. Here invoking these parent functions here in effect return the function which happened to create the nested function here. So along with that, a new closure will be created. So that's all you need to know about JavaScript closure. Now let's discuss benefit of using JavaScript closure. Why we need them so badly. So the first benefit is that it can save partially executed functions. You could see the same inside this example here. Let me get it off these. So we have called this function makeAdder with 5 and the return function here is saved into this variable add 5. Now this variable has a partially executed function. It can be used in rest of the program to add a value to 5 like this. Like this we can add any number to 5 with the same function. Because of JavaScript closure, it can remember the dependent variables even if the variable is declared outside. We have seen the same inside our modular design pattern. From this counter file, we have exported this function increment and the function is using the outer variable counter here. We can make use of this exported function in another files when we import, since this function remembers its dependent variables through its closure. Now actually I can give you more examples from React or Angular. Considering the bigness, I'm not going to frighten you with React or Angular. We'll be making separate tutorials for React and Angular. We'll be discussing these topics there also. Now the second benefit of closure is this modular design pattern itself. It made possible to export a component from a file and importing the same in another file. Since this function is depending upon the variable counter, the function creates a closure, and that's how when we invoke the function in another imported files, it remembers this counter, and that's how this function is getting executed. So modular design pattern makes use of closure. We'll be discussing this pattern in a separate session. Now back to our previous example of this counter here. Now the third benefit of using JavaScript closure is that it creates data encapsulation. Inside this function we have this variable counter, and to work with the variable we have these much 4 functions. Now outside this function, this counter is a private data. It can only be accessed with these functions here. Now if you want to prevent this counter variable from getting updated by mistake with this set function, you can remove this function from here and the problem can be solved. So this is how data encapsulation can be implemented. So that's all the important benefits of JavaScript closure. Sorry for the interruption, a quick message. In this JavaScript learning process, we have to discuss object-oriented programming concept or OOP, DOM manipulation, or you could say making a website interactive with JavaScript, then handling HTTP requests and async operation, etc. and etc. All of these will be discussed in one of my premium course. Once it is ready, I will be sharing the links in video description and inside the info card top right corner. Let me know whether you are interested in such a premium course. In this session, we will be discussing IIFE or immediate invoking function expressions in JavaScript, different ways to define them, and each benefits are explained with maximum real-world examples. I think most of you would be surprised when I say with IIFE we could swap 2 numbers efficiently or override existing JavaScript functions, etc. Most of us are underestimating the IIFE. So let's find out what is so special about this expression. Now before getting into IIFE, quickly revising what we have learned about JavaScript functions will be helpful for rest of the discussion. There are 2 ways to define a function. First of all, we have function declaration, which is defining the function with the keyword function and a function name. Inside the function, for now, let's print this a function declaration. Now let's call the function here. Now the second way of defining a function is function expression. So here we have the function 2. Into it we can pass this function expression like this. Inside the function we'll be printing function expression. Let's call the same here. One of the main difference between function declaration and function expression is that in this function expression, the name is optional. We are not passing a name for this function explicitly here, and such type of functions are called as anonymous functions. While defining a function declaration, name of the function is a must. If I remove this function here, you will get this error. Function statement requires a function name. So function name in function declaration is a must. Now let me try something new here. I'm gonna call this function immediately after defining the function here. As always, in order to call a function, we'll be using a pair of parentheses like this. Now to avoid this error, let's uncomment this function invocation. See, without calling this function here, this function is getting called with this expression. So immediately after the function, we call the function, and that's how this message is printed. This is what we call immediate invocation of function expression, abbreviated as IIFE, also known as self-executing anonymous functions. There are some benefits to doing it. We will discuss that in a bit. Before that, let's discuss various ways to define IIFE. In order to make it easy to pronounce, we call it as IIFE. Now inside this left-hand variable here, if there is a return value from this function invocation, it will be assigned to it. From now onwards, it's not a function, it contains the return value from this function invocation here. So that's why we are having this error while invoking the same as before. Inside the variable, we'll be having the value undefined because the function is not returning anything. See? So that's a way of defining and invoking the function immediately. Now this is not how we normally define an IIFE. Of course this is an IIFE, but we use another similar kind of syntax. So let me get rid of this from here. Here we have the function declaration. Let me remove this function invocation here. Let me try to do the same like we have done with function expression. Now if you add a pair of parentheses like this expecting to invoke this function, it won't work because this is a function declaration, not a function expression. In order to convert this into a function expression, we just need to wrap the function with a pair of parentheses like this. See, the function is getting executed. Here we have the output from this print statement here. So this is how we normally define an IIFE. Naming this function is not a problem, but if you invoke the same outside the IIFE, it won't work. This is an expression. The values inside the expression can't be used outside it. So why not remove the function name from here? Now it became an anonymous function. So that's why if we got another name, self-executing anonymous functions. Now instead of enclosing this function with a pair of parentheses like this, we can use any unary operator as a prefix. Just remove these parentheses here. Now you can use any of the unary operator, plus, minus, child, but the common alternative is this not or negation operator. Its effect is same as before, defining and invoking the function immediately. When we consider this unary prefix with the previous wrapping with a pair of parentheses, we are saving a character or a byte. You could say it's a baby step towards minifying the code. For those who don't know minifying JavaScript, HTML or CSS, it's a process of reducing number of characters in the program, aimed to reduce the file size and thereby reducing the application load time. Now it is possible to pass arguments to the function expression here. Suppose here we have a parameter input, and inside the function I would say IIFE your input, and let's print the passed input. Now it is printing undefined since we are not passing a value to this parameter. Now let's pass the argument 3. You see here we have the output. Now it is accessing the argument that we have passed, and it is printed inside the console here. So that's all how IIFE works and different ways of creating the IIFE. Now you might be thinking what benefit it could have by calling an anonymous function immediately after its definition. So this is where all the basics that we have learned so far becomes helpful. So let's discuss the benefit of IIFE or IIFE with appropriate examples. Mainly there are 4 benefits of using IIFE. avoid polluting outer scope, prevents memory leakage, implements modular design pattern, and finally minify and reduce scope lookups. Now let's look each of these benefits one by one. First of all, avoids polluting outer scope. As we introduce more and more variables or functions into a scope, naming them with a unique and meaningful name becomes difficult, and it will get more worse when we unintentionally or by mistake overwrite an existing variable or redefine an existing function. It is very common when you are working in a big project. Maybe these variables or functions are created in other files by other developers. Now to quickly demonstrate you the same, here we have two script files. First one is this script.js itself, and here we have the second file which is script2.js, and both of them are added into this index.html with two separate script tags. Now inside this script.js, let me get rid of this. Instead I will paste this program here. We have two variables, first name and last name, and here we have the function get full name to combine both first name and last name. Now let's check whether these variables or functions are accessible from our second script file here. Before doing that, I will just print the message here from file 2. Now back to our source tab here, let's put a breakpoint in this line here in second file. So expand this. So here we have the file script2.js. Let's put a breakpoint here and let's reload the application again. Now you could see the scope for this application. We have two scopes, script and global. All of us are aware of global scope, but this script scope here will contain the variables that we have defined in our script files. We are running these JavaScript codes within the script file that is added into this index.html here. So whatever variables that we have inside these script files will be added to this script scope here. As you know, you can directly run JavaScript code within the script tag of the HTML. So whatever variables declared directly into this script tag here will come under this global scope, and the variables declared within these script files here will come under this scope script. But there is an exception for var variables. If you are defining var variables inside these script files, it will come under this global scope here. If you want to see the same, let me change this var. Let's save this and reload this application. So currently these two variables are var variables and this function is const, and let variables or functions will be there inside this script scope. Let's reload the application now. See, currently inside this script scope we only have the function get full name because it is defined with the keyword const, and rest of these two variables, var variables, will be there under this global scope here. See, here we have the first name and last name. So nothing related to IIFE. I just want you to know how this script scope works. So let's change this back to let. Now back to our script2.js file here. Let's reload this application again. So as you can see, the variables that we have declared inside this script.js is there under this scope script. Now let's define another variable, full name. Save this. Let's reload this application again. See, the new variable is also added to the same scope script. Independent of where these components are defined, they are accessible across these two files here. That makes the rest of the problem. So this first file will be managed by one developer and this is managed by another developer. As you can see, inside the same scope we have a function to return the full name from first name and last name that is declared in this first script file, and here we have the second file with this variable full name. As you can see, the contained scope is already polluted. Now this will get worse when we modify or override the existing variables declared in other file. Problems like this will arise if we are not treating it properly. So let me save this and reload this application again. Let's put a breakpoint here and let's run up to the. As you can see, the first name is updated to ASTF. It was initialized with this name here, which is updated inside the second file here. Problems like these will arise as this scope get bigger and bigger. Now in order to prevent this from happening, one way is to enclose the whole code within an IIFE. So here we have the IIFE. So here we have the anonymous function. Now let me copy this and pasting here inside the second file. Now let's enclose the whole code with this IIFE. So everything is trapped within an IIFE. Let's do the same inside the second file also. Now whatever variables or functions declared inside this IIFE can't be accessible outside. Let me save this and reload the application here. Now this time you could see a different scope which is local. It is referring to the local scope or the function scope of this anonymous function of the IIFE. Now with these assignments here, we can't override these variables here. So that's how IIFE prevents the pollution of contained scope. This is often implemented in JavaScript libraries. For example, jQuery or underscore. For those who don't know, these are popular JavaScript libraries created to make JavaScript development more easier and productive by introducing their own methods. For example, here we are at the jQuery download page, and let's download the jQuery file here. So this is how a minified source code looks like. Now let me select all of these codes here. Now let's unminify the library here. So I will go to this website unminify.com. Let's paste the code here. Now click on this unminify button. Let me copy all of this and let's paste the same inside a new tab. As you know, jQuery is a big library. As you can see here, it consists of around 4,000 of lines of code. After collapsing the big session inside the library, the entire library can be seen here. And here we have the IIFE to wrap the entire library. Here we have the anonymous function from the IIFE, and the arguments for these parameters are passed here. So as the first argument, the window global object is passed. As a second parameter, here we have the large function which is taking most of the lines of code from the source code, and it is accepted with this second argument t here, and later in the code it is called here. So that's how this IIFE works. Now back to our topic. Whatever variables or functions defined inside this library does not pollute the project where it is imported. So that's the one reason behind enclosing the JavaScript libraries with an IIFE. There is one more reason for wrapping a library with an IIFE. We can get into that in a bit. Now let's talk about the second benefit of IIFE, which is preventing memory leakage or early release of memory. So back to our script file here. When we create variables or functions, there will be memory slots allocated to them in the form of either the value of the variable or the closure of the function. It is made sure that the memory slots allocated for them must be available as long as these components are necessary for the program. But when we use IIFE, the memory allocated for the variables or functions inside them will be released into free space immediately after its invocation, because those components won't be available outside the IIFE here. So for procedures or set of instructions which are only meant to execute at once, IIFE would be the best choice because it will prevent the memory from getting more and more obese. Let's try an example of swapping two numbers. Here we have two variables num1 and num2. They are initialized with 5 and 8 respectively. Now we have to swap these variables here. That means we have to assign num1 with 8 and num2 with 5. So first of all, we'll print this initially num1 and num2. Now let's try different methods that we already know for swapping two numbers. So the first method is using a temporary variable like this, temp, and first of all we'll assign it with num1 because we are going to assign num1 with num2. Then after that the previous value of num1 will be lost. So first of all we'll save the value of num1 to temp. Now we can confidently assign num1 with num2. Now let's assign num2 with the previous value of num1, which is there inside this variable temp. Now let's check whether it is working or not. Let me duplicate this line here. Now let's move this to the last line here. Finally, see, the values from the variables are interchanged. So this is one way of swapping two numbers. In one of our previous sessions, while discussing destructuring assignment syntax, we have learned a new way of swapping two numbers, which is creating an array like this with num1 and num2. Now we will be using the destructuring assignment like this, num2, num1. So the value from num1 will be assigned to num2, and then num1 will get the value from num2. So this is a simple way of swapping two numbers with destructuring assignment. Now let's do it using the IIFE. So this is how I create an IIFE. We have two pair of parentheses, and let's add the anonymous function here. So here we have the function expression. Instead of this, you can also use an arrow function like this. Now for this anonymous function, we have two parameters, a, b. Now this is what we do. Into this anonymous function, we'll be passing arguments as num1 and num2. So the value from num1 and num2 is copied into these parameters a and b respectively. Now we just need to do this. Num1 is equal to b, and then num2 is equal to a. See, it is working perfectly fine. I'm not saying this IIFE way of solving this problem is better than this destructuring assignment here. I don't know which one is better. I didn't test the benchmark. Even though we are creating two parameters for this anonymous function, the variables or parameters inside the anonymous function will be discarded immediately after invoking the function here. So this is how we can make use of IIFE for procedures or set of instructions which are only meant to execute at once. Now let's talk about the third benefit of using IIFE. It helps to create modules like we implement with modular design pattern. While discussing JavaScript closure, we have briefly explained how modular design pattern works in JavaScript. First of all, inside the index.html, we will be importing the script.js file like this with this attribute module. Here we have the counter.js file. From that, we have exported this function increment with these keywords export default. So the exported function can be imported with an import statement like this. Import increment from the given path. And we can call the function increment like this. We can mimic the same with immediate invoking functions in JavaScript. For example, let me print this sample my plugin program here. So here we have the IIFE. Within it, we have this anonymous function. One of the important aspects of modular pattern is that it helps to expose the necessary parts and keeping the other components private inside the module. See, inside this counter.js file, this function is a public function because the same function can be imported anywhere inside the application. But inside this counter.js file, we can have any number of private variables or functions which are only accessible inside the file here. The same can be achieved with an IIFE like this. Here we have a private variable and a private function. From this, we are only exposing these functions here, public function 1 and public function 2. So this IIFE will be immediately invoked here. So this returned object with these two functions is assigned to this variable here, my plugin. Now from now onwards, you can treat this my plugin as a module. From that, we can only access these public functions, function 1 and function 2. And this is the second reason for wrapping the entire JavaScript plugin like we have seen inside this jQuery plugin here. So inside the library, there will be functions or variables, both private and public. Only public methods or variables will be exported. In jQuery, everything is exported with this name jQuery. So once we import the library, everything can be accessed with this name jQuery. In short, we commonly use this simple $simple like this. So that's how IIFE helps to create modules like this. Now let's discuss the final benefit of using IIFE. Minify and reduce scope lookups. Let me get rid of these codes here. Now suppose we are enclosing our code with an IIFE like this. Here we have the anonymous function. So far in our previous sessions, we have been using this log statement so many times. Now I just want to reduce the number of codes that we write for this statement. So I'm going to provide a short version for this, like an alternative name. So let me copy this and I will pass this as an argument to this IIFE here. Now let's remove this. Now instead of this, we just need to use log. So from now onwards, in order to print anything into the developer console, we just need to call this function log and let's pass the message here. See, it is working properly. So inside this IIFE, we can use this function log as an alternative to this console log function here. So this is a simple example through which we can reduce the number of codes that we write. So it can be treated as a step towards code minification. Once you learn DOM modification with JavaScript, the method document.getElementById is a common function. You can provide an alternative name for this method like this console log. Now let's keep this aside. I will just comment this. We will get into this later. Now let's check how IIFE reduce scope chain lookups. While discussing JavaScript closure, we have talked about scope chain. Consider this program here. We have the outer variable or global variable x and then the parent function outer function. It has a variable y and then the inner function with z variable and then the parent function with the variable y and then the inner function with the variable z. Inside this nested function, we are trying to print the value of x. Now this program can be transferred to this scope chain here. The nested function, inner function with Z, then outer function or parent function with Y, global scope with X. Now the same can be represented like this. We are accessing the variable X, which is actually defined in global scope. Now JavaScript engine has to map this X variable to its definition. So first of all, it will look whether the variable is defined inside the nested function. No, there is only one variable Z. Then it will go to the immediate outer function, which is the parent outer function. There is no variable with the name X. Then it will go to the immediate outer scope, which is global scope. There we have the variable X. So this is what we call scope lookups. To avoid this scope lookups, we can use IIFE arguments. Let's check how it works. Now for this anonymous function, I will be adding this parameter global. Into it, I will be passing the value window. So this window is the global object in client-side JavaScript programming. And we are assigning the same into this parameter global. Since we are wrapping the entire code with this IIFE, we can access window with global like this. So whenever JavaScript engine see global, it is directly mapped to the window object so that it can reduce the scope lookups up to the definition where it is defined in the JavaScript library or the implementation. And there is one more benefit of using this alternative name global for this window here. As I said, window is the global object in client side. When you work with the server side Node.js application where the global object is named with the same name global itself. So when you work with server side or client side simultaneously, so you can avoid the mistake of referring the global object, since everywhere the global is mapped to the global object, whether it is client side or server side. Now to even simplify this name, you can even pass G here. And for the same reason of reducing the scope lookups, we provide direct mapping with these global objects like document, which is a common object when you work with DOM handling. We will be getting to that while discussing DOM manipulation, means modification or altering the HTML elements with JavaScript. So in those situations also, we are mapping this global object document directly with this parameter like this. Document, you can provide the entire name to reduce the scope lookups, or you can pass simple variable names like G, D, etc. While discussing jQuery, I have mentioned that the entire library is exported with this name jQuery, and the same is simplified with this shorthand symbol here, $, which is already defined inside the library. Now to reduce the scope lookups, we just need to do this. jQuery is mapped to this $, so that you can avoid the scope lookups. Now I hope you understood how IIFE helps to reduce scope lookups. Now finally, let me show you how to override an existing function in JavaScript with IIFE. So here we have the function console.log. For example, I will extend this function console.log with an additional feature. That is, along with printing the message, I just want to append the date and time of executing that statement here. For that, we can define a function like this here, function, and this function accepts a single parameter, say message. Inside the function, we will call the original function console.log. Whatever message passed to this function will be printed. As a prefix for this, we will be appending the date and time. So I will do this new date. To format the same, I will just call this function to local time string. Now let's separate them with a colon like this. Boom, it is working fine. See, whenever we call the function log, it will call this function that we have passed here, because we are passing this function as an argument to this log here. So the message, whatever we pass here, will be accepted with this parameter here, and the same is prefixed with the date and time at the time of executing this log statement here. So with IIFE, we can extend or override an existing function. Now it's time to discuss how a program is getting executed within a JavaScript engine. Before that, we need to understand few prerequisite topics. That's what we do in this session. First of all, you should know the relation between ECMAScript and the JavaScript engines provided by different web browsers. Suppose we have got a JavaScript file, say script.js. Where do we run it? We need a platform or an environment to execute the program. often called as runtime environment. If you have experience in other programming languages, you should know this. Prior to start writing the program, we'll be installing a runtime environment for the particular language. For example, for the language Java, we have to install Java Runtime Environment, often abbreviated as JRE. That of C# is .NET Framework. Like that, all programming languages have a runtime environment. Prior to executing these programs in these languages, we have to install this runtime environment. Do you recall installing any such runtime environment for the language JavaScript? No, because it already comes with web browsers, whether it is Google Chrome or Mozilla Firefox or Microsoft Edge or any other web browsers. Now, once we run the program within these web browsers, independent of the browser we choose, the output from all these browsers must be the same. That's the job of browser manufacturers. I will explain. Mainly, there are two engines in a web browser. Rendering engine, which is responsible for rendering HTML and CSS files. And then we have a JavaScript engine to read and carry out the JavaScript program that we write. And these engines are not referring to something like engines that we see in automobile vehicles. It is another software like any other runtime environment. So each browser manufacturer has to develop their own engines. The JavaScript engine of Google Chrome is V8, that of Firefox is SpiderMonkey, Chakra is the engine in Microsoft Edge. Now, to get uniform output across these engines, standardization of the language JavaScript is a must. And it is done by ECMA International's TC39 committee. They specify rules and guidelines to implement the language, which is called ECMAScript. This includes language syntax, semantics, libraries, and complementary technologies. These topics are commonly discussed in a JavaScript beginner's course, things like data types, variables or functions, operators and their features, etc. Now, browser manufacturers develop the JavaScript engine in accordance with these guidelines in ECMAScript, so that independent of the browser we use, the output of a given JavaScript file will be same across these browsers. This is often rare in the case of other programming languages. Most often, the environment for running a program is developed and maintained by a single company or entity. For example, Java Runtime Environment is created by Oracle. The runtime environment of C#, which is .NET Framework, which is developed and maintained by Microsoft. This is not the case with JavaScript. The rules and guidelines are specified in ECMAScript. It is a written document. And then we have these multiple browsers to implement the runtime environment or engine for a single language JavaScript in accordance with the ECMAScript. Since these web browsers are creating their JavaScript engines on their own, ECMAScript components and features are implemented in these web browsers in different ways. Sometimes that might be a problem. Some of the latest ECMAScript features might not be available in some web browsers, so you have to compensate that in your JavaScript programs. But when you think about the competition between these browsers, it's a good thing. These browser manufacturers are competing with each other to come up with a faster JavaScript engine. Currently, V8 is the fastest and popular JavaScript engine, which is used in Google Chrome and Node.js server-side applications. So for rest of the discussions regarding JavaScript behind the scenes, we'll be using V8 as a reference, though other JavaScript engines work almost in a similar fashion. Now let's talk about the role of a JavaScript engine. First of all, it should provide all the data types, operators, objects, and functions specified in ECMAScript. And the rest of the important things are left to the engine manufacturers, such as compilation or interpretation, execution of the program, memory allocation, garbage collection, etc. We will be discussing each of them later. Now let's talk about the second point which you must know before learning how JavaScript works. As I explained in one of my previous sessions, consider the following code written in JavaScript. The symbols we use, numbers and operations in this program is unknown to computer machine. It can only understand binary code consisting of zeros and ones. The process of converting our code in a specific language to machine-readable format is called compilation or interpretation. Before moving forward, let's briefly discuss what is compilation and what is interpretation. In compilation, first of all, the program is translated or compiled into an intermediate code, or most often referred as object code. Then whenever you want to execute or run the program, you use this intermediate code. So compilation is a two-step process. The source code is translated once. From then onwards, the intermediate code is used to execute the program. Since code compilation or translation is done before the actual execution of the program, it is also called ahead of time compilation. Languages like C, C++ are compiled programming languages. If you had experience in these languages, you know that there are two commands to run the written program. For example, here we have got a C++ program and we are compiling it with a GNU compiler, and this is the first step, and we will get the intermediate code in the format of an exe file. Then whenever you want to run the program, just execute the exe file, you will get the output, which is the second step. Now let's talk about interpretation. It is a single step process. To be precise, in interpretation, code execution is a part of code translation. No intermediate code is created. For example, languages like Python, PHP, even JavaScript comes under interpreted languages. But there are some corrections to make, which I will explain in a bit. Now consider this Python program. It is getting executed with a single line of command. That's it. Like that, when you want to run a JavaScript program in client side, we add them into HTML file with a script tag. The JavaScript file gets executed while rendering the HTML. For those who worked in Node.js knows that JavaScript files are executed with a single command like node, the name of the JavaScript file. Either way, whether it is on client side or server side, it's a single step process. During interpretation, translation and execution happen one line at a time. Since there is no intermediate code, each time when we run the program, the interpreter has to translate the program before the actual execution. While in compilation, the whole code is translated or compiled to intermediate code in one attempt without a pause. So while comparing it with interpretation, the compilation is faster. No need to translate the program each time when we execute the program. The translated binary code is there inside the intermediate output. Now, one of the major benefits of interpreter is that the code execution environment can be made more flexible because both the translation and code execution is happening simultaneously. Because of that, the interpreter has access to dynamic runtime informations, like which part of the code is taking more time to execute, duplicate procedures, etc. and etc. So optimizing generated code at runtime is possible in interpretation. And for the same reason, these interpreted languages like Python, JavaScript, etc. often does not follow a line-by-line execution. They make adjustments to overcome the delay in the process of line-by-line interpretation. Now here, JavaScript does something brilliant called just-in-time compilation, or abbreviated as JIT compilation, where the interpretation and compilation are merged to overcome the demerits of interpretation. Now let's look at what is happening behind the scene when you run a JavaScript file within the popular JavaScript engine V8, which is found in Chrome web browsers and in Node.js applications. Though there are other JavaScript engines, once you understand how V8 works, then you could easily compare its working with other JavaScript engines. Now enough with the introduction, let's get started with the topic. So first of all, here we have the major components in V8 engine, and the picture shows how they process a JavaScript file. First of all, we have a parser, which is the first step in translating any human readable program to a lower level or machine readable code. The main objective of a parser is to check whether the program is written according to the JavaScript language syntax rules. If not, then the statements not following the syntax rules must be shown as an error with necessary details. The steps that we follow in a programming language parser are exactly what we follow when we learn new spoken languages like English, Spanish, German, etc. Consider the following sentence. To make sure whether the sentence is correct or not, we take the complete sentence and we will separate the parts of the sentence into subject, verb, object, etc. And then we will check whether the sentence is constructed according to the grammar of the language. In English, it follows the grammatical rule, subject plus verb and followed by the object. So it's a valid sentence according to English language. This is what we exactly follow in V8 parser also. There are two stages in a V8 parser: lexical analysis and syntactic analysis. Through lexical analysis, the whole program is scanned and broken down into different components, often called tokens. like identifiers, operators, keywords, literals, etc. like we have done with our English sentence. And during syntactic analysis, we check whether the generated tokens forms a meaningful JavaScript expression with the help of JavaScript syntax rules. Now let's explain the same with a JavaScript program containing the function getFullName, which takes an object as a parameter consisting of first name, middle name, and last name properties. And then the function returns the generated full name with the given names. Since middle name is optional, we have a ternary operator to append the same in between first name and last name if it is present. And here we have called the function with sample names. For rest of the discussion, only this function declaration is used. Let's check the life cycle of this JavaScript function within V8 engine. So the whole process is starting from this parser. Inside the parser, first of all, we have lexical analysis. During lexical analysis, the whole program is broken down into different tokens. As you can see inside this function declaration here, function and return will be marked as keywords, and then whatever names or labels that we use to refer components inside the program comes under identifiers, such as function name, parameter name, property from the object, etc. And these concatenation operators comes under the operator. And whatever the fixed values inside the program, like these white space or empty string, comes under literals. And rest of the simples, whether it is closing and opening of these parentheses or curly brackets or these colons or question mark, comes under punctuations. So in this way, the whole program is converted into a stream of tokens. And these tokens are the input to the next stage, which is the syntactic analysis. During this syntactic analysis, we have to check whether the written program is correct or not with the help of JavaScript syntax rules. To do that, during syntactic analysis, the whole program is represented in a data structure like this tree here. And this tree-like structure is called as abstract syntax tree, often abbreviated as AST. So let's check how this tree is created from this function declaration here, and let's check how this tree helps the parser to check whether this written program is correct according to the syntactic rules. So let's start with this root node itself. First of all, parser identifies this function definition as a function declaration. That's what we have inside this root node here. And then the body of the function is wrapped within a pair of curly brackets. As I mentioned before, everything wrapped within a pair of curly brackets is what we call block statement. Inside the function, we only have a return statement, so that's what we have here, return statement. Now, if you look into this expression, we have multiple operations. But inside this AST, we will consider one operation at a time. So that's why we have this binary expression, meaning we are only considering two operators at a time. So this plus operator is referring to this concatenation operation here. So on the right hand side, we have this member expression, meaning we are trying to access a member or property of this object. So that's pretty simple. Now on the left hand side of this concatenation operation, we have a big expression. At a time, one operation is considered like we have done here, and that's how this subtree here is generated. So here we have the binary expression, meaning it is representing this concatenation operation. On the right hand side, we have this ternary operation, which is often called conditional expression. On the left hand side, we have another concatenation, and that is what we have expressed with this binary expression. See a simple concatenation between this first name and this white space here. Now when it comes to conditional expression, we have three parts. So first of all, we have the condition here. If it is true, meaning if the middle name is present, then this expression is executed. That is what we have expressed with this binary expression node here. Just a concatenation between middle name and white space. If middle name is not present, an empty string is returned. That's what we have here. So three parts of the conditional expression. So the whole program is represented with this AST data structure. Now how this AST helps the parser to check whether the written program is correct or not. For that, the parser will check the syntactic rules from the leaf nodes of this tree here. For now, we'll just consider the operator. Here we have a concatenation operation between these two strings. So it's valid according to the JavaScript syntax rules. But instead of this plus operator, suppose we have a multiplication operator, it won't work because multiplication can't be done with two strings. So the whole program execution will be stopped and the error will be shown with necessary details. But in this program, we have a concatenation operation between two strings. It is valid. The result of this concatenation will be again a string. Now, when it comes to this conditional expression here, whether this condition is true or not, it will return under the string. Because here also we have concatenation between two strings, it will return a string. Here we have a literal string, so whatever the value of this expression here, it always returns a string type. Then again we have a concatenation between string and string, which returns another string, and here we have the final concatenation. So the whole process from leaf to the root node will be verified. For the sake of this explanation, I have only considered the operator and the type of its operand. But in a real life, there are a lot of things to be considered when it is verifying with the JavaScript syntax rules. So if all of them is correctly verified from bottom to this root node, and that's how a parser identifies whether the written program is correct or not. So after this parser, we have this abstract syntax tree. Now the program should go through ignition interpreter and turbofan. And this is where the important task of an engine happens, which is the translation of the program into a lower level or machine readable format. And this is where JavaScript engine manufacturers implement their intellectual ideas to make the engine more efficient. In brief, ignition interpreter converts the program to a lower level bytecode. And when necessary, this bytecode will be converted to machine code using this turbofan here. Before getting into further explanation of ignition and turbofan, I want to remind you with something. Before V8 version 5.9, instead of the compilers, ignition and turbofan, full code gen and crankshaft were doing these operations. Not a change of name, they were different in action also. Don't confuse with these terms, I just want to explain what's the reason for this change. So full code gen was the baseline compiler, meaning the compiler where most of the translation is done, where the program is converted to architecture specific machine code. No optimization was done during this process, so all of the optimization are left to the crankshaft. The original motive for switching from this configuration to the new architecture is that the output generated by full code gen was consuming 1/3 of the RAM, especially on mobile devices. Once it is replaced with ignition interpreter, the generated bytecode shrank by a factor of 9 because the bytecode generated by ignition is more concise. Now let's look at what is really happening with ignition and turbofan. As I said, the output from ignition interpreter is a bytecode, where all the operations are specified with these commands similar to the assembly language commands. As I said, the generated bytecode is more concise compared to the previous full code gen output. But how can we execute this bytecode when our machine can only understand binary codes with zeros and ones? To execute the program, this bytecode is interpreted by an outside interpreter, which does what these instructions imply. So that's how a statement is getting executed in V8 engine. Now what does this turbofan do? Because after ignition itself, all necessary steps like translating and executing the program is done. Here turbofan handles the optimization of the bytecode when necessary. Let me explain. During the program execution at ignition interpreter, it monitors or saves runtime profile information and feedback. Based on that, frequently executed part of the program is marked as hotspot. Suppose if our function is getting invoked multiple times, then it will be marked as hotspot. Then this information is passed to the turbofan so that it can convert the corresponding bytecode to architecture specific machine code, which gives the maximum speed for the hotspot, which in turn makes the hot program to execute at a much faster pace. In this way, turbofan ignores generating machine code for procedures that are less frequently executed. It saves both memory and time. Turbofan not only converts the bytecode to machine code, but it also does various optimization techniques. I will explain few of them. If you want to know more about them, you can go through the reference that I have given in the video description. As the execution progresses, the ignition interpreter collects the analysis information or feedback of various operations, mainly the type of input for an operation. It will be helpful for further optimization of the program. I will be explaining this with an example. Once the engine categorizes inputs for an operation into different types, turbofan can optimize the operation for a particular type of input, so that it can avoid unwanted steps involved in the operation if same type of input comes in subsequent runs. This type of optimization based on assuming same type of input in subsequent runs is called speculative optimization. And here we'll be discussing these two optimizations, hidden class and inline cache. Consider accessing a property from an object. It might look easy for us, but for the compiler it's not. For example, the given object might be undefined or there is no property with the given name. The property is not present in the object, but it is in the prototype, means it is inherited from other object, etc. By considering the fact that JavaScript is a dynamically typed language, this becomes even complicated, means the developer can modify an object anywhere in the program later. So to make such operations more efficient, V8 engine creates hidden classes. You might be familiar with classes from other languages where we have to specify the structure of the data upfront. Such type of user-defined classes helps the runtime environment of such languages. Now when you create a JavaScript object as you wish, internally V8 engine creates hidden classes to store the necessary information of the object. And these are called as inline caching. So inside the inline cache, there will be hidden classes stored. So for the first time when V8 engine encounter an object like this, the corresponding hidden class will be saved into the inline cache. Inside that, we'll be having the structure of the class. In subsequent runs, when we pass another object with same structure, then V8 engine can make use of the already saved hidden class of the same type, and it can make use of the necessary informations required for accessing properties from this object and other informations also. Here these two objects is having the same structure, so that will be another hidden class. Now accessing properties from these objects becomes more easier because all the necessary information is there inside the inline cache. Since this object is matching with the already saved hidden class, it helps the engine to avoid lot of the overhead. If you want to access the first name from this object, suppose the object is saved at the address XP, then in order to access the property first name, you just need to use the offset 50. So accessing properties becomes more easier. Like this, there can be a lot of information helpful for the subsequent runs of the same type of object. Now let me explain how speculative optimizations like this becomes helpful. Now consider objects with only these two properties, first name and last name, as a parameter for this function. Suppose to this function getFullName, we are only passing objects with these two properties, first name and last name. So V8 can create a corresponding hidden class with these two properties, first name and last name, and the necessary information will be saved in inline cache. Now here comes the speculative optimization. Since there is no property middle name, this entire operation can be skipped. So a turbofan will convert the bytecode of this function without this middle name to this architecture specific machine code here. Now that's how speculative optimization works. Now remember this, the machine code that we have just generated is only applicable to the hidden class with these two properties, first name and last name only. When an object with these three parameters are passed, the optimized machine code will be bailed out because it is not matching with the optimized hidden class. Bail out the optimized code, and the corresponding bytecode will be used to execute the function. So that's how speculative optimization works. To dig deep into the topics that we have discussed here, you can refer the video description. I have given the necessary reference there. Now if you want to see image illustrations or image nodes like these, I will be uploading image nodes like these from our JavaScript beginners tutorial on our Instagram handle @codeaffection. So please consider following us on Instagram also. I don't know how to emphasize the importance of this topic in learning JavaScript. Call stack and execution context sum up every concept that we have learned so far. Here we're going to discuss what is call stack and what is an execution context. With execution context, we can explain how var variables or function declarations are made available even before their declaration, which is the harvesting behavior. And then most importantly, JavaScript closure is redefined and its importance are explained with the help of execution context. In previous session, we have discussed how the JavaScript engine translates and optimizes a JavaScript program. Finally, here we're going to discuss how the translated program is getting executed with the help of execution context and call stack. While executing a JavaScript program, the JavaScript engine treats the program as multiple functions, and the rest of the part outside call functions, let's call it as global environment for now. Each of these parts are executed separately. But you know what? JavaScript is a single-threaded language, meaning it can only execute one part at a time. To manage the execution of these parts, JavaScript has something called call stack. It's a mechanism to store and manage currently executing functions. What function is currently being run and what functions are called from within that function, etc. are coordinated within this call stack. Call stack is also called as execution context stack. You will understand how it is called so once you learn what is execution context. Now let's see how this call stack mechanism works with an example. Now what I am going to show you is the brief details of call stack. You will get the full picture of call stack once you learn execution context. So here we have a program to find average of given numbers. Here we have three functions: find sum, find average, and print average. We have called this print average function here with an example array. Inside this print average function, the given numbers is printed as the inputs and the average is printed here. For that, another function, find average, is called here. Inside the function, in order to find the average, sum of given numbers is divided with the number of elements. To find the sum, we have called another function, find sum, where the sum of the array elements is calculated with this for loop here. Now let's look how call stack manages the execution of this program here. For that, this function will be divided into four parts. We have three functions here and one global environment. So the execution starts with this line here, print average from global environment. So first of all, into this call stack, the global environment will be pushed. In order to execute this line, we have to invoke the function print average. To execute this function, we have to push the same into this call stack here. So the first line here prints the input as the given numbers. Now inside the second line here, it is calling another function, find average, to find the average of given numbers. So in order to execute this function, we have to push the same function to the call stack like this. Now inside this function also we are calling another function, find sum. Finally, this function find sum is pushed to the call stack. Okay, so we have global, print average, and find sum in call stack. For this global environment, the execution is paused at this line here, and that of this print average, the execution is paused at this second line here, and for this find average function, the execution is paused at this first line here. Now at any given time, the top item in a call stack is the currently part being executed. So currently this find function is the currently executing function, and inside this it will calculate the sum through this for loop here. There is no other function to call. Finally, this function calculates the sum of given numbers and it returns the sum back to the caller. So once the execution of this function is over, it is popped off from the call stack. So we have removed the top item from the call stack after its execution. Okay, now the topmost element inside this call stack is find average. So the execution of this find average can be resumed from where it is paused before. So that will be this first line here. Now we got the sum of given numbers. It is divided with the number of elements. So we get the average. We done with the execution of this function also. It returns the average back to the caller. Now that's also deleted from this call stack. Now the topmost item in this call stack is print average. The execution of this function is paused at this line here, second line here. So the execution starts from there. We got the average. Now the average will be printed with this log statement here. At the end, we are done with the execution of this function print average. Now we can continue with the global environment execution. But unfortunately, there is nothing left to execute after this function invocation here. So we are completed with the execution of the program and the call stack is empty back to its initial state. So this is how call stack coordinates the execution of a program. Now there is one thing you should know. This call stack is implemented in a JavaScript engine with a data structure. And you might have already noticed this. The last inserted item inside this call stack is the first item to be deleted. So this type of data structure is called as last in first out, or abbreviated as LIFO data structure. So that is what we have mentioned here, LIFO data structure. As you already know, JavaScript is a single-threaded language. Hence there is only one call stack. Always the top function is the part currently being executed. Rest of the functions are waiting for the functions inserted after them. So far we have discussed the simple explanation of call stack. To get the full picture here you need to familiar with execution context. Before that, let me show you how this call stack is coordinating the execution of program within the developer console itself. So here we have the same program with same input, and finally we got the average 23. Now let me show you the call stack within this developer console here. So first of all, let's switch to this sources tab here, and we have to put the breakpoint at this function invocation here because this is where every execution starts. About that, we have function declarations, and the execution of those functions start with this function invocation here. Now let's reload this. So the execution is paused at this point. Let me expand the call stack, and currently you could see this anonymous. It is referring to this global environment here. Now I will use this step button here so that we can see the step-by-step execution. So the execution reach up to this function here. In order to execute this function, first of all the function must be pushed to the call stack here. See, now this line here can be executed without calling any function, so that is what we have printed here. Now in order to print the average, first of all we have to invoke or execute this function find average. Now so the same function is pushed to the call stack here. Now in order to complete this statement execution, we have to invoke the function, another function find sum. See, that is pushed to the call stack find sum. It is finding the sum of given numbers using the for loop. At the end, we got this sum and it is returned to the previous function. The function find sum is popped off from the call stack. Now the sum can be divided with the number of elements. After that, this function execution also stopped and it is removed from the call stack. Now the execution of this function print average can be resumed from where it left off. So the average will be printed with the log statement using the return value from this find average function. So you could see the same here. We got the average output here. Now there is nothing left in this print average function, so it is popped off from the call stack. Now we only have this global environment and there is nothing left to execute, so execution of the program is over. Now finally call stack is empty. Now hope you understood how call stack coordinates the execution of the program. Now let's look what is execution context, and let's check how it can provide further details on how things are executed within this call stack here. And most importantly, the execution context explained how the concepts that we have learned so far implemented in a JavaScript engine. Actually, in order to execute these functions, we need much more information. For example, in order to execute this print average function, we need the arguments passed to the function, and the definition of this function console.log is not present inside this function. It is also defined outside this function. Other than that, when this function calls another function, the execution of this function is paused. Finally, after execution of the functions just above this function completes, the execution of this function must resume from where they left off, which is this second line here. So all of those information are required for the execution of these functions here. So without such informations, we can't execute these parts inside the call stack here. So that's what an execution context does. So an execution context is an environment where JavaScript code is evaluated and executed, which keep tracks of runtime evaluation of the code. So this is how execution context is defined. To be specific, these are execution context, not functions. So I would like to redefine this call stack here. It's a mechanism to store and manage currently executing execution context. So that's why this name we have here, execution context stack. Now let's look what are there inside an execution context. Basically, it has some states. For example, this code execution context denotes whether this execution context is suspended or currently being executed, etc. And here we have another state, script or module, meaning whether this execution context representing code is from within a module or not. If it is not there inside any module, then it will be denoted as a script. Like this, there are various states to denote or represent the state of the execution context. Now here we have the important part in an execution context, which is lexical environment. We have already mentioned this term in previous sessions. Lexical environment consists of two things: environment records and reference to outer lexical environment. Inside environment records, we have mapping of identifier to variables or functions. For example, we have this variable sum. We name sum, or the technical term is identifier. So this identifier is mapped to its value 0. We have this function. Every function is of the type object. To be specific, all functions are of the type function object. Okay, so this function object will be mapped to this identifier find sum. So that's what we have meant by this identifier mapping. And then we have arguments object, which consists of the values that we pass to parameters of a function. You will see them in a bit. Now we have to map this keyword. In global environment, it will be mapping to the global object inside a function. For a function execution context, it depends on how the function is invoked. We have discussed this keyword in brief in previous sessions. More about them will be discussed in future sessions. And finally, we have this global object. Client-side application, this will be window. In case of Node.js applications, the global object is called as global itself. And finally, we have this reference to outer lexical environment. So if a parent calls a child function, the child execution context will be referring the parent here. Okay. Now I'm going to show you how the concepts that we have learned so far implemented with execution context. Before that, I want to tell you this: execution context is created in two phases: creation phase and execution phase. First of all, creation phase, then execution phase. This is where the program or the context is getting executed. So here we have the first example program. Here we are calculating the area of a circle. Here we have the constant pi radius, and we are calculating the area with the equation, and we have called the function with the given radius. Now first of all, we are in global environment. So it is called as global execution context. So first of all, the global execution is pushed to the call stack here. So currently global execution is in creation phase, meaning in creation phase the program is just scanned from top to bottom. In global execution context, we have this global object. This is only seen in global execution context, and which is window, since we are dealing with client-side applications. In this context, this will be mapping to this window object. Now let's start this scanning from this first line here. We are declaring a constant variable pi. Constant variables are not created or added to the execution context during creation phase. So next line, we have a var variable r. Var variables are added in creation phase, but they will be initialized with undefined, not the value that we have provided here. And here we have the mapping for this function here. The function object for this function will be saved, and the identifier here, calculate circle area, is mapping to this function object here. With this statement, we are calling this function, so it won't be executed during creation phase. Only the mapping are done during creation phase. And finally, we have this outer lexical environment. There is no outer lexical environment, so it is having the value null. Now we are going to enter into the execution phase of global execution context. This is where the program is getting executed. So the first line, it is creating a constant variable pi, and it is initialized with the given value here. And we have the var variable r. It is assigned with the value that we have given here. Here we only have a function declaration, so there is no execution. The execution will be done when the function is invoked. So this function is called here. So the execution of this global execution will be paused at this line here, and the control of execution will be moved to the new execution, which is function execution here. So the new execution context is pushed to the call stack, and for that execution also we have those two phases: creation phase and execution phase. Statements inside the function will be scanned in creation phase. Let and constant variable are not created during creation phase, so there is no mapping for this variable area in creation phase. This keyword is mapping to window, and here we don't have the global object mapping. And here we have the arguments object. It's a special type of object, meaning the 0 here is referring to the first parameter here, and which is assigned with the value or argument, first argument 5 here. We have an outer lexical environment, which is global lexical environment. During execution phase, so here we have the first statement. It will create the let variable area, and the area is calculated with this equation here, and it is assigned to the variable. And the same will be printed to the developer console with this log statement. Now we are done with the execution of this function, so the function execution context will be popped off from the call stack. Now we can receive the execution of global execution from where it is paused, which is here. Since there is nothing left to execute inside this execution context, it will be popped off from the call stack. Finally, we are done with the execution of the program and this call stack is empty now. So this is how execution contexts are created in real time in two phases, creation phase and execution phase. And you see inside this call stack, we have currently executing execution context. Now with what we have explained, I can prove the hoisting behavior of var variables. So back to the VS Code. Now here we have the same program. So here we have the area of a circle with the given radius 5. Now in order to show you the hoisting behavior of var variables, I'm gonna try to print the value of var variables prior to even declaring the variable. So let's try to log the variable r here. See, here we have the value undefined. Now if you try the same with this constant variable pi, you will get this error, cannot access pi before initialization. So this is what we call hoisting behavior of var variables because they are available to access even before their declaration. Now it can be explained with this execution creation here. During creation phase, constant variables or let variables are not created. Only var variables are created, initialized with undefined, not the value that we have provided here. This value 5 will be assigned during execution phase when the execution reach up to this line here. Before this line, the value of this r variable will be undefined from the previous creation phase here. Now let's move this line to here. Now you could see the value 5 is getting printed here because while executing this line here, the undefined will be replaced with the actual value 5 here. So from here onwards, the value of r will be 5. Before that, the value of r is undefined. So this is what we call hoisting behavior of var variables. There is one more important thing. You can access any function declaration even before the declaration. It's because of the same reason. We are calling this function here after declaration here. Now this will even work if you move this function invocation before the actual function declaration here. See, it's working fine now because the actual function is created or function object is created in creation phase itself and it is mapped to the corresponding identifier. For the same reason, even before starting the execution phase, the function declaration is already saved in the memory. So it is available reference, and then we have this variable x, and we have this outer function mapped to the corresponding function object. Then we have this lexical environment assigned as null. Here we have the execution context of outer function. This is mapped to window. Arguments object for these two contexts are empty because there is no parameter. Inside this outer function we have this variable y, and then we have the reference to inner function object, and here we have the outer lexical environment reference as global lexical environment, and here we have the innermost function inner function, and here this keyword is referring to window. Arguments object is empty, and here we have the local variable is it. The outer lexical environment is referring to the outer function lexical environment, which is this one here. Now here we are trying to access this variable x. So first of all, it will check whether the variable is available inside the local lexical environment. It's not. There is only one variable is it. Then it will look for the outer lexical environment, which is here. We don't have the variable is it here. Then it will look for the outer lexical environment of this outer function, which is this global lexical environment. Here we have the variable x. So and this is how the outer variable made available inside this inner function here. So this is what we call scope chain. All of these lexical environment are interlinked with this outer reference here, and you should know this. There is no separate thing like scope chain. Scope chain is implemented with this reference here. This scope chain is the same reason for accessing this function console.log here. This log function is not defined nowhere inside these two execution contexts. It's actually defined inside this global object window. So because of these scope lookups from here to here, using these references, we can access the functions that is defined inside the JavaScript libraries anywhere inside these nested functions. So hope you understood scope chain. Now I'm gonna explain closure with the help of execution context. And let me tell you this, understanding how execution context works is the best way to understand how closure works. So here we have the same program that we used to explain closure for the first time. So here we have a function. Within that we have this variable a. From this function we are returning another function, and inside this return function we are accessing this local variable a here. We have called the function here, and the return function will be mapped to this variable print a here. After thousands of lines, the same return function can be accessible with the variable here. That's not the problem, but how it is made possible to access this variable a, which is not present inside this function when the actual created execution context is deleted already. By the time when you call this function after thousands of lines here, the execution context of this function is already deleted, meaning the environment that is saved the value of this a is deleted already. Then how it is made possible to access the value of a at this stage here. So let's start with global execution context creation phase. Scanning from top to bottom, function mapping is there, and then global object, and this keyword is mapped to window. Constant variable is not created during creation phase, and there is no outer lexical environment. Now moving to the execution phase of the global execution context. Execution reach up to this line. This is where we calling the function. So the execution of this global execution is paused at this stage. New execution context of function fun is added to or pushed to the call stack. It is in creation phase. This keyword is mapped to window. Arguments object is empty. Outer lexical environment is referring to global lexical environment. That variable is not created in creation phase. Now here we have the execution phase. Assume that we are just completed the execution of this line, meaning the let variable is created and initialized with the value that we have given here. After executing this return statement here, a new function should be created, which is this anonymous function, and the execution of this function is over. So it is removed from the call stack. We have already discussed that a closure is created when a function is created. Here this anonymous function is created while executing this function here. So a closure is created here, and the return function is mapped to this print a variable here, and it is mapping to the new closure. A closure is similar to execution context, but there are some difference, so they are called as modified stack. So within this closure we have the function lexical environment. Like we have in previous case, we have the same variable mapping, and the outer lexical environment is referring to this global execution context. We don't need to save the global execution context inside this closure because it's already there. We can access whatever we want from this closure using this outer lexical environment. So currently this closure is having the lexical environment of this fun function here. So the execution is up to this line here. Now after thousands of lines, there might be lot of function invocations, and all of them will be pushed and popped off from the call stack. Once the execution reach up to this line, there will be only global execution context, and then so first of all the closure will be pushed to the call stack, which is having the lexical environment of this fun function, and inside that we have another execution context of this anonymous function, or I will refer it as print a function execution context. So the two phases, creation and execution phase, will be there for this function also. Assume that we are in execution phase of this print a function here, and when the execution reach up to this line here, we need to find the value of a. The value of a is not present within the local execution context here, so the outer reference is pointing to the lexical environment within this closure where we have the variable a, and this is how it is made possible to access the closure. And here I forgot to mention something here. Once a function is returned from this statement, a closure is created, and the execution context that created this closure is removed from the call stack. So this closure will be saved somewhere inside the closure because this closure is referring or mapped to this variable. As long as there is a mapping with this closure, it should be saved somewhere in call stack. And you should also know this, a call stack is not a flat array to just push and pop when you want. Actually in a JavaScript engine, it will be implemented using a linked list or hash map data structure where you have the possibility or provision to save other list of data like this closure here, so that whenever needed, like this situation here, it can be pushed to the call stack here. So once the execution of this print a function is over, both of this closure and local execution context will be popped off, and there is nothing left in this global execution environment to execute, so everything is clear. This is how closure works. See, the environment that is required for the execution of this function is there inside this lexical environment and here also. The closure save or remember the execution context for this function's execution. That's what we have here, closure. This is the only way to remember the dependent variable of this function somewhere in the memory. Without this closure, when the time is to execute this printf function, we won't be having the execution context that actually created the variable a. It is already removed. Immediately the execution of this line is over. The same environment with some modification, preserving what is important for the rest of the execution, is saved inside the closure. That's why we are calling it as modified stack. Is saved somewhere inside the call stack. When the time arrives to execute the function here, it is again pushed to the call stack. See, here we have the entire scope chain. From here to here, closure, and from here to here. Now that's all about execution context. Now I want to tell you one more thing, which is stack overflow. Consider this program here. We have a variable I initialized with 0, and here we have the function busted function. Within that we are incrementing the value of I, and then we will print the value to the developer console. And here we have a while loop. Within that, condition is false, so no iteration is executed. Once I change this condition to true, this function will be executed without an end. Because of the same reason, the call stack will be filled with the execution context of various invocation of this function from this while loop here. Now to show you the same, I will change this to true. Now you could see that this function is executing indefinitely. Let me show you the task manager here. Now you could see that the memory allocated for this Google Chrome is getting incremented in a rapid phase because of this indefinite function invocation. It will end up in stack overflow, meaning call stack will be pushed with indefinite number of execution contexts for this same function here. This is what we call stack overflow. Now calling a function again and again with different inputs each time is the best way to solve a particular type of problems. So that's what we do with recursive function approach. Executing a function again and again in a controlled manner. More about recursive function will be discussed next. While running this program, if your Chrome browser is entered into a not responding state, you can end the execution with this task manager end task button here. The concept of recursion will always be complicated if you don't know how it operates and why do we need them so badly. In this session, we have covered recursive functions in JavaScript in depth with the help of real-world examples. And most importantly, the evolution of call stack while executing the recursive function using self-explanatory diagrams. Let's start with the definition itself. Recursion is the act of function calling itself. Recursion is used to solve problems that contain smaller sub-problems. I know this definition itself is a confusion. And if you have gone through other materials on recursion before, you might be feeling like an endless function execution chain. Don't worry, we are going to put an end to this endless play. Now staring at the definition won't be helpful enough. Instead, let's go for a thorough inspection with few sample programs. Now, suppose we want to write a JavaScript program to reverse a string and assume that we are not allowed to use any impl functions. How will you do it normally without recursion? Most of you might have thought about doing it using for loop or any other loop like this. So here we have the function reverse string. Here I have used this prefix underscore just to indicate this is the normal way of solving this problem. In a bit, I will be writing a function using recursion without this underscore. Okay, now let's call this function with this string morning. This function returns the reverse string like this. So I have to put this function call in a log statement like this. See, here we have the reverse string. Now for this function we have this parameter input, and here we have a local variable to store the reverse string, and here we have a for loop just to iterate through characters inside this pass string here. So it starts from this character G, it is saved to this local variable here. In next iteration, the second last character N will be appended to the result. Like that, this for loop will concat the characters inside this string in reverse order, and that's how a string is reversed reverse inside this function. Now let me show you how to write a recursive function for the same problem. First of all, how could we say there is a recursive way of solving this problem? It's already mentioned here. Recursion is used to solve problems that contain smaller subproblems. Now I have an idea to split this solution into smaller subproblems. So let's try to solve this function using recursion. So here we have the function reverse string. We have a single parameter input, and here we have the function body. I'm going to split this function like this. Okay, get first character. I want to make this first character as the last character, and that's how we reverse a string, right? First character as the last character, and then rest part of the string should be called for another reverse operation. So reverse rest of the part. Okay, this is how I'm going to split the function into smaller subproblems. So first of all, we have the return keyword. Now first of all, let's retrieve the first character from the string. For that, we can call this string function char at. So this will retrieve the character at the index 0, which means the first character from the string. Now we have to find the reverse of the same string excluding the first character, and we have to append that just before the first character. So for finding reverse of a string, we'll be calling the same function, and that's why we are calling this function as a recursive function. Now inside this function, we have to pass the string excluding the first character. For that, we have a function called substring. So input dot substring. Now what this function does is it will take the substring from the index 1, which is here, starting from this O to the end. So the entire string excluding the first character is passed to this function here. Substring. We have discussed these functions char at and substring in our separate JavaScript string tutorial along with other string functions. Now this is how we split the solution into multiple subproblems. Now assume we are calling this recursive function with the same input morning. During the first invocation, the first character m will be here, and rest of the string which is starting from here to here should be passed to the next call here. And in that function call, the first character O will be taken out, and rest of the part will be passed again to the same function reverse string. And this will go on until there is nothing to pass to this function reverse string, and it will happen once the invocation reach up to this last character here. In that case, this parameter will be having an empty string. To handle this case, we will be having an if clause like this. If input is equal to an empty string, we just need to return an empty string like this. Now a condition or a clause like this is necessary to stop the further execution of this recursive function. If there is no such condition here, this function will be indefinitely called without an end. So in any recursive function, we need such an end condition like this. Okay, now let's try to reverse this string using recursion. So I will just remove this underscore, and here we have the recursive function called. Sorry, we have a typo here. Boom, that's it. This string is reversed using this recursive function here. Now you can try this function with your name, or you can try with a palindrome like race car. A palindrome is a word which is same even after reversing it, like race car or mom or dad, etc. Let's try the same example morning, and let's check what is happening behind the scene. I will be explaining how this function is getting executed using the step-by-step approach, and finally I will be explaining the same with the execution stack and stack frame. So first of all, we have called this function reverse string. Okay, reverse string, and in short I will type it as reverse. Into this function we have passed morning, and during the execution this return statement is calling the same function with a different input. So I will represent that like this, reverse, and here we are calling the same function without the first character m, and the same character is concatenated at the end. Now let me duplicate this line. Now during this function execution also we have this return statement, right? There also the same function is invoked by removing the first character, and it is appended at the end here. And this process of calling the same function reverse will go on until we only have an empty string to pass to this function reverse. See, finally we have a situation where we only have an empty string to pass to this function reverse. Now what happens when we pass an empty string to this function? This condition here, this if clause will be executed and thereby it will return an empty string, right? Let me duplicate this instead of this function. Now we can replace this function invocation with an empty string. That's it. We don't have any function to invoke because of the limiting condition here. Otherwise the function will be invoked indefinitely. So this limiting condition or if clause here isn't necessary, is a must in recursive functions. Now finally the concatenation in this order will result in our final output here. Now I hope you got a brief idea on what is happening behind the scene when you execute a recursive function. Now it will become more interesting if we explain it using execution stack and stack frame. So here it is. During the first invocation of the function, there will be a stack frame like this. It will end up in calling the same function with the same input by excluding the first character, and the same excluded first character is appended at the last. So this is the first stack frame added to the execution stack. Now to execute this function, a new stack frame is pushed. There also the same function is invoked with a substring excluding the first character, and it is appended at the end. So each time we call the same function, the same operation happens. Okay, and finally we will reach in a situation where we only have an empty string to pass to the function reverse. In that case, this limiting condition or if condition will be reached, and for that function invocation an empty string will be returned, and finally there is no function to invoke, and that will put an end to calling another function. So here we have the last stack frame. It is having the value empty string. Now after returning the empty string, this stack frame will be removed, and this function is returning the value empty string, and that empty string is concatenated with this G, and it will end up in this string G here. Once we are done with that concatenation, we can remove this stack frame also. So this stack frame will be deleted in a moment. Here we have the concatenation result G, and which is the value of this function called here. Okay, and that G will be concatenated with this N, and it will end up in this value Gn. And this process of concatenation and removing the topmost stack frame will continue until there is nothing left in this execution stack, and finally we will get the reverse string. So this is what happening when you call a recursive function. It will end up adding more and more stack frames when you call a recursive function, because we are calling the same function again and again until it reach up to a limiting condition. All of the function execution in between will be added to the execution stack in the form of stack frame or execution context. Now let's check few more common problems where we can use recursion. Now let me show you a simple program counting down from a number up to 1, which is a common example to demonstrate recursive functions in JavaScript. So here we have the typical way of solving this problem using for loop, counting down from n. So here we have the for loop to print the numbers starting from this given n up to 1. Iteration variable starts with the given number, and on each iteration it will be decremented by 1 up to the value 1. Now let's try calling this function with a number 10. So here we have the output. It is starting from 10 and it is counting down up to 1. Now let's try to solve this problem using recursion. First of all, we'll be printing the given number into the console. After that, we have to print the next number just below this number. For that, we will call the same function, and we are passing the number just below this given number n. So we are calling this function inside itself. So there should be a limiting condition to block the indefinite function invocation. So here we go. If n is less than or equal to 0, we need to stop the execution of the function. So we just need to pass return here. Now let's check whether it works or not. So instead of this normal way, let's try this recursive function. Boom, it works. Now I hope you understood recursion better from this simple example here. Now some of you might have this question. In previous example of reversing a string, from the limiting condition or if clause we have been returning an empty string. But here inside this if clause we only have a return keyword. Why is that so? It entirely depends on the logic of the problem. In previous example we have been creating a sequence of concatenation of characters in reverse order, and the final result or the the reverse string can only be produced after concatenating all the characters in reversed order. So in previous example, instead of returning an empty string, if we were using just a return keyword like this, the final call of the function will end up returning an undefined. If we were trying to concat undefined with other characters, it will end up in undefined. So in order to avoid that, in the final limiting condition, we are returning an empty string. In case of this problem here, each of the function execution here is independent of the previous function execution, meaning each of the function execution here is printing a different line inside this console window here. So when n is equal to 1, this line will be executed, and thereby this line is printed here, and next function call is called with the value 0, and this limiting condition will be reached. So we just need this return statement to stop the further execution of the function. So I hope you understood how we treated this limiting condition in both of these examples differently. Now there are other problems commonly used for demonstrating recursive functions like factorial of a number, Fibonacci series. Both are related to mathematical concept, then finding sum of digits in a number, etc. These problems can be split into smaller sub-problems as we have done so far. So it's definitely possible to find the solution recursively. Try solving any of these problems and let me know how it goes in comment section below. While explaining the previous example, in our first example we have explained the evolution of call stack during an execution of recursive function. Even though the function is defined with minimum number of quotes, while executing the program, more and more execution context or stack frame is pushed to the call stack based on how lengthy is the input. Suppose in case of this problem here, if we pass 100 here, it's gonna take 100 stack frames. Now let's try 1000. It's gonna take 1000 stack frames to be pushed to the call stack. Now if I pass 1 million here, it's gonna push 1 million stack frames, and finally it will end up in stack overflow because the memory allocated for the call stack is limited. See, here we have the error maximum call stack size exceeded. It's because of the repeated function call causing pushing more and more stack frames or execution context to the call stack. If it exceeds the memory allocated for the call stack, we will get the error. And it's possible for most of the mathematical problems like these involving number. Because in real life, there will be a situation where we need to pass a higher number. In that case, recursive function is not feasible. But in case of problems involving tree-like structures, graphs, etc., recursion is the best choice. For example, consider this problem here. You have given the folder structure and you have to find the empty folders within it. And first of all, we have this my computer, and inside that we have 3 folders representing local disk C, D and E. And inside this local disk C we have an empty folder, pictures, and inside this folder downloads we have the installation file for Chrome web browser. This local disk is empty, and this local disk E is having a folder softwares. Inside that we have the MS Office installation file. Now this folder structure can be represented with this object here. Each of the folders here is represented with an object containing 2 properties, the title representing the name of the folder, and this property children contains the subfolders inside them. So for empty folders like this pictures and this local disk D, the children's array will be an empty array like this. And these files also, these exe files also is represented with the same object, but in case of those such files, the children's property will be null, representing they are a file, not folders. So inside them we don't have any subfolders. Okay. Now we have to find the empty folders and to the path to the folders when we have given a folder structure like this. For problems like this, recursion is the best choice. So first of all, let me get rid of the previous program here. Now I will be saving this object representing the folder structure in a separate variable like this. Let folder structure is equal to this. Now let me collapse this object so that we can see the rest of the actual function, recursive function. So the object is saved inside this variable folder structure. Okay, now let's try the function, recursive function, to find the empty folders within this folder structure. Find empty folders. For this function we have two parameters, object and path, and the default value of this parameter is an empty string. In order to check whether a folder is empty or not, we have to go through each corresponding folder's object, and we have to check the children's property or array whether it is an empty array or not. If it is an empty array, we can say the corresponding folder is an empty folder, and we have to find the corresponding folder path also. So this object here is representing the outermost folder, which is this my computer. So first of all, we will check its children property, and this children is of the type an array. So we have to check each of the object or each of the folders within it. So we'll be using a for loop here. So index I, and the number of iterations will be as much as elements inside the children's array. So we can do this object dot children dot length. If you are already aware of array functions for each, you can use that function to loop through this array here. So here we are going to iterate through the subfolders or children of this object or the parent object passed to this function here. And inside this loop, we'll be calling the same function find empty folders, and here we'll be passing the children object itself. As I said, inside this children array, we'll be having object representing the subfolders here. The children array of this my computer is having these subfolders. In order to check whether these subfolders are empty, we'll be calling the same function with the object corresponding to these folders here. So we can do this object.children, and we'll be using the array index here. Now we have to pass the value for this parameter path, because that's the only way to remember the path that we have traversed while finding the empty folder. So initially, by default, path parameter is empty, and upon each recursive call inside the function, we will be passing the name of the file that we have covered. So object dot title, which is the name of the folder that we have checked. Finally, we will be appending the / here. So initially, this parameter path will be an empty string, and then as we go down in this folder structure, each of the covered folder name will be appended into this string. So we will execute this for loop here if current folder is not empty. Now let's check whether there is an empty subfolder. Since we are implementing this function recursively, we must provide a limiting condition also. So first of all, we could say if the children property is null, meaning the current object is representing a file like this installation Chrome exe file, or for this file MS Office. So for those files, the corresponding object children property will be null. In case of empty folders, it will be an empty array. So we'll be mentioning those two cases in our if clause here. If object.children is equal to null, meaning it's a file. So there is no further inspection needed for a file. So we will just return here. Else if the children array is an empty array, we could say this is an empty folder. Okay, so we can handle that situation here. If children, the length will be 0, right? Now here we can print the whole path to the empty folder path. So this path parameter will be having the path up to the parent folder, and we just need to append the current folder name. So we could do this object dot title. That's it. So this means an empty folder. Okay, now let's call this function with this given folder structure here. Boom, that's it. These two folders are the only empty folders inside this given folder structure. So recursion is the elegant solution for problems involving tree traversing or graphs. Now that's all about recursive functions in JavaScript. So here we are winding up this session. As I said, I'm planning to deliver rest of the topics through a premium course which I will be sharing later. Link will be there in video description and inside the first comment of this video. Thanks for watching this video till the end. If you are not a subscriber already, please consider subscribing. Please like and share this video with your friends and colleagues so that they can also benefit from this. Have a nice day. Bye.